My name is Owen Murphy. I work with Gaelectric Energy Storage. I mainly work on power systems modelling, assessing the technical opportunities for storage and optimising the build of it, sizing the generation capacity versus the storage capacity, etc., suited to a particular system. So just the contents of what I'm going to go through. I'm going to run through the background of the company and just the history of the collaboration between ourselves and the ERC over the years. The Virtue Store project, that was a project done, it was an SEI funded project done between ourselves and the ERC, and I'll do some background to Case on our project in particular. So, Gaelectric Energy Storage was founded in 2006, member of the ERC since 2009. We've recently got our 10th hire this week, just in the storage team. We're part of a wider company that has an extensive portfolio of wind on the island of Ireland. Our flagship project is Case, compressed air energy storage in Larne, in County Antrim, Northern Ireland, with a generation capacity of 268 megawatts. So the history. Around 2009, 2010, we began some Wilmar modelling with the ERC. That was before the FORS study, so before a lot of the technical challenges to the system were highlighted by the TSOs. Following that year, after the publications of the FORS study, we did some more analysis with Wilmar. All 2010, we did some analysis of flywheel on the island, and most recently, between myself and Jodie Dillon and Ciara Dwyer, we carried out an extensive study called the Virtue Store project. It's a study of storage in the system in 2020 using Plexus. So these are the main results of that study. So we kept it to very generic characterization of a technology. So it's technology neutral, so you assess the trends of how storage would operate in the particular system. So here are the 4 scenarios that we studied. We basically just changed the generation capacity and the storage volume, and reran them within the Plexus model to see where the benefits lie. First key result is that reserve was a key driver. I've another graph on the next slide which will go through this in more detail. But reserve is a key driver of the value that storage provides to the system. The second one is that we varied the installed wind capacity and found that the value of storage increases significantly as more wind comes on, and it's not a linear it's not a linear relationship, because every extra megawatt that's installed in the system during a curtailment event will be curtailed itself if you don't have mitigation. So here are the system benefit of storage. So you can see that there with the high and the low wind and the slightly lower wind scenario, you can see the benefit, that's production cost and change in interconnector costs, goes from 2.1% to 2.6% when you change the wind by just about 700 or 800 megawatts. We found that the installed capacity is more important than the energy density, so megawatts are much more important than the megawatt hours. Now that's just in the Irish system. If you reran the model for a different larger system, you may have a different result. And a large scenario A there, we found that would reduce system costs, its production costs, plus change in interconnector import costs would be 30 million in the year 2020 alone. But again, as more wind would come onto the system, that value should increase. And there you see the breakdown of the benefit of each scenario. So these are results of some sensitivities that we carried out to validate the model. It was carried out by Jodie Dillon, and what it looks at the value of storage as various constraints are added. So as you go to the right, you you add a constraint each time and you see the value. So the value here at the end is cumulative. So you see the first one, that's the traditional storage model where it's basically arbitrage load shifting, very conventional, almost archaic view of what storage does. It's a lot more than that. These two are the TCGs, that stands for transmission constraint groups, so basically the minimum generation levels on the island, such as minimum number of plants online, 2 plants in Dublin for reactive power, etc. So we added those constraints in and assessed the benefit. The third one we added in was the non-synchronous penetration limit, which was, in this study we used 50%. So we added that in and assessed the effect. And the last one is reserve. So you can see that a large chunk of the value that storage provides to the system is true reserve, i.e. true flexibility. And so case. Once that study was finished, we used, I took the model and developed it and put in case. So this is our project in Northern Ireland. So up to, on the top of your screen here that says GDL2, that's the license area that we control for the Triassic salt, which is the shallower seamless salt, which will be used to put the caverns of case in. Now, for anyone not familiar with case is you have a compression train that compresses air into an underground cavern in a salt chamber, and that's held as a pressure difference overnight or for a few days, and it can be re-expanded through a generation train and generated the next day. And this is our project in Northern Ireland. So we have 268 megawatts of generation with 200 megawatts of compression. That's 2 separate units, as opposed to a pump storage would have a turbine that would pump and or generate, and might have a series of them. We have 2 completely separate trains. Our storage capacity is 8 to 11 hours, and some key dates: we will be drilling to verify the thickness of the salt and to finalise the cavern structure in the summer. Further clarification at DS3, that's a very important milestone, and planning we'll be going for around this time next year. So I took the core model of the study that we did with the ERC through the funding of SEI, and I put case in it. And I used slightly different methodology since the completion of the Virtue Store study. The third DS3 consultation came out where they outlined how they modelled the system in Plexus. What I did was I run an unconstrained schedule to get the interconnector flows, fix those flows into the dispatch run, which is the constrained one, the one with all the market constraints, reserve constraints, etc. We used the non-synchronous penetration limit of 75% and fuel and carbon prices from the IEA World Energy Outlook 2012. So the key findings. Found a system benefit of 21 million, a reduction in curtailment of 41 gigawatt hours, and that's based, the results of this particular run was curtailment was 1%, which is quite low. We would expect that to be between 2 and 4%, say, for a non-synchronous limit of 75%. A key one is reduction in number of starts of...
Just 1 minute.
Okay, sure. 26% reduction in the number of starts of the conventional fleet, which, if you look at that system benefit value of 21 million, that would be an externality to that, because you don't take into account extending the lifetime of the conventional portfolio. Also, one of the key things as well is that this is for 2020 alone, and that as a 30 to 40 year asset, and as more wind comes on the system, those benefits should increase also. So just this is the last slide. Taking the Irish experience, and we're seeing a lot of huge penetrations of wind now. and other systems around the world should see PV penetrations or wind penetrations just as high in coming years. And we are starting to see that soon. So Italy has deteriorating system inertia, has a ramping requirement of 15 to 17 gigawatts in just 2 hours in the evening. And most significantly, I think, is the reduction in POR availability of up to 30% in just 4 years. Germany, similar stuff, a lot of plant cycling predicted, reduction in secondary operating reserve availability, and EMBW at World Energy Storage Forum just 2 weeks ago in Berlin presented analysis on what you would have to do to withstand a 14-day period of calm wind. And they estimated that you would need about 23 terawatt hours of storage once their wind portfolio is built out to actually cope with that 14-day outage. Currently they have 0.04 terawatt hours. And lastly, Spain. If you see the demand curve, it's actually quite similar to Ireland, but the morning ramp is very severe, and also you have curtailment during the nighttime valleys to keep plants on, to keep them for the morning ramp. And all these in Italy, Germany, and Spain are all very similar to the issues that we're seeing currently and those outlined by the DS3 program.